Hi everyone, welcome back to Dave's Math channel. Today I'm going to do another just kind of popular video on math. I'm going to talk about pH. What is pH? I'm sure you guys have all heard of pH. It's basically how acidic or how basic a solution is. But it has a mathematical definition, which I want to get into. Anyway, so let's begin. So what is pH? Let's first define it mathematically. Well, like I said, I mean, just let me first talk about qualitatively a little more detail. So pH is really it stands for power of hydrogen. The capital H stands for hydrogen, the little p stands for power. So it's kind of an acronym. And it usually ranges from about 0 to 14. I think it could sometimes go below 0 or above 14, but this is very, very rare. I mean, 0 is about as acidic as you could possibly want. If you put your hand in a acid that was pH of 0, I think your skin would get burned. And the same thing about pH of 14. So you don't want to handle that strong acids or that strong basic solutions or alkaline solutions, as they're called. So anyway, 7 is right in the middle. 7 is neutral. So you kind of have an idea. I mean, if you look back at this picture, these is just kind of pHs of familiar substances. I'll get into this more later, but you can see that it goes from 0 to 14 and 7's right in the middle. They're also color coded. I'll get into that too. But how do we define it mathematically? Well, what we do is we measure the concentration, what's called the molar concentration of hydrogen ions, H plus ions. And technically, it's not really H plus ions, because an H plus ion, if you study chemistry, that's just a proton. And protons don't exist by themselves, not in solutions anyway. They get attached to a water molecule. They actually become what's known as hydronium, which is H3O plus. So technically, pH is really it's a measure of the concentration of hydronium ions, H3O plus ions, in a solution. And the mathematical definition is it's the negative of the base 10 logarithm of the molar concentration of hydronium ions, if you like. So, for instance, a pH of 7, which is neutral, that's water, that would mean that its molar concentration is 10 to the minus 7. 10 to the minus 7 moles per liter. This quantity H plus with the brackets around it, that's the molar concentration of H plus. In general, quantity X with brackets around is just the molar concentration of X. So if the molar concentration is 10 to the minus 7 moles per liter, that means the pH is 7. Similarly, if the molar concentration was anything else, like if it was 10 to the minus 5, it would have a pH of 5. If it was 10 to the minus 9, it would have a pH of 9. So on. So that's the mathematical definition of pH. And here's a good kind of diagram showing pHs of common substances. I guess the most acidic pH you might encounter is the acid inside a battery. They use sulfuric acid inside batteries, and you wouldn't want to touch that stuff. Like I said, it's very corrosive. You could get burned. And you especially don't want to swallow it. That could kill you. So stay away from stuff with pH of 0, even 1, I think. So 0 is the most acidic. 1 is pretty acidic, too. That's the acid inside your stomach. It turns out your stomach has hydrochloric acid in it. And that's how you digest food. That's how the food in your body, when you eat, that's how your food gets digested. It gets burned by the hydrochloric acid in your stomach. And that's how your body metabolizes energy from the food you eat. And then lemons. Lemon is probably about the most acidic thing you might want to eat. I've actually eaten lemons. I kind of like how they taste. Most people can't stand eating a lemon because they're so sour. I like sour fruit, and I've even eaten lemons from time to time. It's not easy to eat a whole lemon, but sometimes when I go to a restaurant, if they put a little slice of lemon inside my drink, I'll eat the lemon, and I don't mind that. And then what else you got after that? Soda has a pH of 3. So, now, pH of 3, I think most people can handle. And most of the food you eat actually is acidic. Tomatoes have a pH of 4. I guess, what's the next one? Coffee has a pH of 5. Milk has a pH of 6. Milk is pretty close to neutral. That's why, acidic stuff tastes sour. That's another thing about acids. They taste sour. And I guess the lower the pH, the sour they taste. That's why lemons are so sour. Oranges are pretty sour too. I guess oranges probably have a pH of about 3, maybe Granny Smith apples too. That's my favorite apple, by the way. I like sour apples. And then water's right in the middle. That has a pH of 7. It's neutral. And then above 7, we get to alkaline solutions or basic solutions, if you like. And what's next? Blood. Your blood in your body. It's not really pH of 8. These are sort of rounded. I think your pH of blood is more like 7.35. It can vary a little bit, but it's supposed to be close to 7.35. I think somewhere between 7.3 and 7.4 is healthy. If it's below, so I'll get to this later, but you don't want, your blood has a very well regulated pH, and you don't want it to get outside of that range, that very tight range between about 7.3 and 7.4. But it is slightly basic. And then what else you got? pH at 8, I guess egg. Yeah, egg yolk is basic. And then what's next? Stomach. I can't even read that one. Something with your stomach. And then ammonium. Then you get these solutions that are basic. Soap is pretty basic. I mean, the good thing about bases, they're good for washing. Like with soap, when you take a shower or when you wash yourself, you're washing with soap which has a pH of about 12. You wouldn't want to eat it because it's very basic and it would taste very bitter if you try to eat it. That's the thing about bases; they taste bitter. Acids taste sour, bases taste bitter. But beyond 11, you probably don't want to eat anything with a pH above 11. You don't want to eat soap. You especially don't want to eat bleach. Bleach or again, 13 and 14 is toxic, so you wouldn't want to drink bleach, and you certainly wouldn't want to drink drain cleaner. Drain cleaner is the most basic thing there is. That's why it's good at cleaning your drain. It's corrosive, just like the strongest acids are corrosive. Strongest bases are corrosive, but the nice thing about strong bases is they're useful for cleaning things. So, anyway, that kind of gives you a overview of the pH scale. And you might wonder, I wondered this for a long time. Why does pure water have a pH of 7? So it's kind of nice we have the scale from 0 to 14, but how did it turn out that way? Well, the reason that's true is because of something known as a reaction rate constant of aqueous solutions. It turns out that whenever you have chemical reactions, I don't know if it's every kind of chemical reactions, but a lot of chemical reactions have this constant associated with them called the reaction rate constant. And it turns out that aqueous solutions, any solution that has water in it and other chemicals, if it's an acidic solution or a basic solution, it always obeys this equation 1. It says that the concentration of hydrogen, H plus, times the concentration of hydroxide, which is OH minus. And by the way, that's why bases are strong too. I mean, because they have a lot of OH minus. They have a very strong concentration of OH minus, just like acids. Strong acids have very strong concentration of H plus. So it turns out the product of these two concentrations is constant. It's about 10 to the minus 14. Of course, it's temperature dependent. This is actually only strictly true at 25 degrees Celsius, which just happens to be close to room temperature. I guess it's a little warmer than room temperature. It's about 77 degrees Fahrenheit, I guess. That would be maybe a sunny day at the beach, But anyway, at that temperature, this product is equal to 10 to the minus 14. So for a neutral solution, like water's neutral. It has the same concentration of H plus and OH minus because there's no preference one over the other. There's no other chemicals in it if it's pure water. And then that's why pure water has a pH of 7. Because the concentrations are equal. They're both very small. They're only 10 to the minus 7, so they're kind of difficult to measure. But there is a non-zero concentration of both H plus and OH minus, even in pure water. It's not pure H2O. you have these H pluses and OH minuses just because the water molecules are kind of bumping into each other every now and then. One of the electrons will come off of one of the hydrogen atoms, one of the water molecules, and it'll attach itself to another. So that's basically what's going on. It doesn't happen very often, but it does happen, and that's why water has a pH of 7. Anyway, I thought this was really interesting when I first learned this. And how do we measure pH? Well, I think most of you probably have heard of litmus paper. This is probably the most commonly known way to measure pH. I think there's other devices. You can use electrodes from batteries to measure pH more accurately. I actually did that when I was in college. But if you just want a rough estimate of how acidic or how basic a solution is, just stick a piece of litmus paper into it. And the nice thing about litmus is it changes color. And the color it changes depends on the pH of the stuff you dip it into. I think there's different kinds of litmus paper. They don't all follow this color pattern, but this particular kind of litmus paper they're showing here, I guess if you dipped it in an acid, it would turn red or orange, depending on how acidic it is. I guess the most acidic, it would be a very deep red, and then the most basic, it would be a very deep blue. So, yeah, most litmus papers like this. Acid turns it red, alkaline solutions turn it blue. If it's in the middle, at least for this type of litmus, it turns green. I've seen other litmus where it's just yellow or even not even colored at all. But anyway, there's different kinds of litmus, like I said. But depending on the litmus paper you're using, you can get a pretty rough, at least within a pH of 1 or so, you can get an idea of the pH of the stuff you're measuring, which I think is kind of cool. And I mentioned batteries a few minutes ago. Why do we want really, really strong acids? Well, the main reason is for batteries. Because what acids do in a battery, they have a lot of hydrogen ions in them, and the ions will produce electrolysis in the battery. That's how the batteries work. So you have these two metal plates inside a battery, and I guess they're different kinds of metal. Like usually use copper and I think zinc. And the copper attracts, if I remember this correctly, I think the copper attracts positive charges, and the zinc attracts negative charges. It might be the other way around. But that's how batteries work. They create a electric current when you stick a couple electrodes in, and then you attach a wire to those electrodes. That's how you generate electricity. It was actually the first way electricity was generated. I think it was Volta who invented the first battery around 1800. And I think we've been using very strong acids for batteries ever since. And so that's why you don't want to open up your car battery and stick your hand in, but anyway, so strong acids are useful for batteries, and they usually use sulfuric acid, which is a very strong and pretty horrible acid. But anyway, and how do you neutralize acids or bases? Well, this is interesting. I'm kind of a novice on this. I don't understand this completely myself, but there's these things called buffer solutions. And I think what those are is you put like a salt in your solution. The salt helps to neutralize the solution. So you can pour a really strong acid. You could pour hydrochloric acid, I think, or even sulfuric acid into the right buffer solution, and the solution, I think, the salt will take care of most of the strong ions in the acid or base, and they'll neutralize them. So buffers tend to have the same pH,D or very close to the same pH,D if you add a lot of acid or a lot of base to them, and that's a very useful property. And there's different buffers with different pHs. I guess both buffers have pHs near 7. That's neutral. But there's also acidic buffers and basic buffers, and they work the same way. Kind of nice. And your blood's an example of a buffer solution. And like I said earlier, your blood has to have a very regulated pH. I guess it's around 7.4. I think I misspoke earlier. It should be between 7.35 and 7.45. That's normal. So, and most of the time, I think most people's blood is in that range of pH. But sometimes it can get off balance. I mean, there's something called acidosis, which is where your blood becomes too acid. I guess 7 is pretty serious, and 6 means you're going to die. And similarly, if it goes too basic, you get what's called alkalinosis. I'm not sure what causes this, by the way. Maybe it just means the buffers in your blood aren't working properly. I'm not an expert on this, but anyway, you don't want your blood. 7.8 is serious, and nine means you're gonna die. So that's the pH of your blood. It has to be very well regulated. And this also depends. I'm just going to say a little bit more about this. That's why you don't want to eat. You want to eat well. That's one reason you kind of want to watch your diet, not just so you don't get fat, but also you got to watch that your body doesn't produce too much acid or too much alkaline. I think it's very common for people to have slightly too acidic blood. I actually watched a video on this a few years ago. Most people eat too much. It doesn't mean they eat acidic food, but they eat food that produces a lot of acid. I think we tend to prefer eating foods that make a lot of acid in our body. Like meat makes a lot of acid, I've heard. Actually, it's funny because like citrus food, like lemons and limes, even though they have a very low pH, I read that they actually don't produce acid in your body. They're actually good for you. And salad's good for you too. I've heard vegetables tend to raise the pH of your blood. And if you don't eat enough vegetables, which I don't like vegetables that much, and I eat a lot of meat. The problem with that is that I guess people who eat too much meat and not enough vegetables, they're in danger of getting acidosis. Because what happens is your body works harder to maintain the pH of your blood. If that happens, it usually does stay maintained. But then your blood's working harder. I think that can increase your blood pressure. And also, I think it can make you more moody, more irritable. That's why it's better to have a good diet because it helps to balance the pH of your blood. I do drink alkaline water, by the way. I have some right here. It has a pH of about 9. And I've heard it's good for you. And I don't mind how it tastes. So I think it's a good thing I'm drinking alkaline water. It's probably helping maintain the pH of my blood. But anyway, I guess that's all I want to say for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.